So this is a footbridge. This is the River Tyne. Newcastle is a place, it's on the, it's right at, there's a big port and they build ships there. Very industrial city, bombed to smithereens during World War II because it was the industrial heart of UK. But the bridge is a walking bridge and it actually, the footpath goes down. Right now it's half up like this because it has to go up because all of these ships that go through on the river. And the other bridges are like from Middle Ages, you know, so it's just kind of a, it's really out of care, it's out of time and it's out of, it's just out of place, out of time, but it's a beautiful little bridge. And I just thought that was, it's just a different kind of a design, but it's designed to do that rotating thing. So that you can walk on it or you can have a ship go under the bridge. And then probably the last one, this is down on Willwood.
That's what it looks like right now.
That's what it looks, this is, okay, this isn't,
Is that the
yes,
bridge?
that's what I'm trying to remember. This is not what you drive over now. This is what you used to drive over. So I was off to the side and I don't remember when I took this picture if the new bridge was constructed or not. I mean, because there's a different pathway. This still exists. But I don't know if the Warren, if the truss is still there, the Warren Truss. I think it is. I'm pretty sure it is because the maintenance guys go over it. But yeah, at that time, one of the things that's really interesting that Willwood, so this diversion dam provides all of the irrigation for the Willwood irrigation project. And all the water for all the irrigation projects in this part of the world comes from the Buffalo Bill Dam up at Cody. So this is actually a diversion dam on the Shoshone River. And it's really, it's interesting for a lot of, I also take pictures of this for fluids because it's very, very interesting. However, when they built this in the 1920s, nobody ever had any idea that we would have equipment the size that we do now. You know, everything, I mean, everything was small. Most people were walking or taking, you know, horses or some little Model T kind of a thing. And so bridges became bridges. So if you went into civil engineering, bridges actually have a planned obsolescence. They build them for about 15 to 25 years because we don't know what's going to happen next, right? Roadways are built for more like 50 years, but there still is a planned obsolescence because we don't know what everybody's going to visit upon us. Another example of planned obsolescence, it wasn't planned, but that I just think is really interesting, doesn't really have a lot to do with this class, but the Panama Canal had to be, they had to do a major renovation project on it. The Panama Canal was successfully completed in the very early 1900s. And it's a series of locks that ships have to go through. And over time, ships got bigger and bigger and container ships could no longer actually go through the Panama Canal. So they had to refurbish the Panama Canal maybe 20 years ago so that the larger ships could go through it. So, and I haven't seen it yet. I intend to. I've been jealous of people who've gone to see it.
Well, I think they were looking at having to do it again for well, it wasn't quite cargo ships, but cargo ships keep getting bigger and bigger, right?
Yes,
And the Panama Canal is again the one that's constricting it for both trade
exactly.
because all the businesses want to make sure they get through the one in Egypt, the Suez.
Yes,
And
yes,
so-
exactly. Because otherwise you have to go around Cape Horn if you're in
Yeah.
Africa, or you have to go, or Cape Good Hope,
Yeah,
Cape Horn, or whatever. I'm probably mixed up.
because there's now there's a couple ones down by the South America. I think it's Cape of
I'm looking at the map back here. I have to go
I
look.
don't remember if it's I don't remember which one.
I know. I think here's Africa, right? I think this is the Cape of Good Hope. And I believe this is the Cape Horn. But you can see how far up, I mean, I know this is,
Yeah.
there's the Panama Canal. And if you can't go through there, you have to go clear around
Clear
South
around,
America.
yeah.
Yeah, same with.
Yeah, this is Cape Good Hope.
Thank you, I got it. I got it, all right.
Isn't Good Hope, or is it one of them like Death Sail?
Yes, right,
I
here,
think it's-
the Cape Horn
Yeah.
is because the Atlantic and the Pacific Oceans come together. And so it's very true, and it's squeezed, you can't see it here, but if you had a map of, the South Pole, all the water has to go through this constricted area, you know, so it gets very fast, very turbulent, lots of stuff. And that's actually why I read this back in the old days when people went through that on clipper ships, why sailors had earrings. If you went around, if you successfully lived when you went around the Cape, you did an earring, so it was like pirates, not pirates, but sailors were telling each other, I have done the thing, you know? So, yep, so anyway, I think, in my opinion, bridges just are the coolest thing in the whole world. It just really, what happens with bridges is, how would I describe this? The bridges are a function of a particular time and place, and people built them based on local things and things that were rooted in time. So every time you see a bridge, that's why I think the Millennial High Bridge in Newcastle is so interesting to me, because like all the other bridges are like, they're like old bridges, right? They're like made out of masonry and they're made out of stone, and they've got the tower, and then you see the Millennial High Bridge and it's like totally out of time for that. So it's very interesting to look at.
So when we did go to Chicago when I was a senior,
Yeah,
and they had a whole bunch of bridges just like that, the Warren one.
the Warren Trust, yeah.
But
sure.
they have like cables on them. and they-
Yes, because everything has ships going through it, you know, and this is so interesting too, because I realized this about myself. I'm not going to make any assumptions about you guys, but my family, when they came to the United States, it was in the middle of the 1800s, and they got off the boat and they got on the train, and we never went back. My family's been in the American West for over 100 years, and there's no water. I mean, there's water, but not navigable water like that, you know? And so like if you go to the Upper Peninsula of Michigan, or you go to Chicago, or you go to any city in Europe, everything's about the river and the bridges and getting stuff through. So it's just amazing, you know, it's just amazing to see that. And I always feel kind of like a very unsophisticated person, because I don't even have the words to describe water, you know what I mean? It's so out of my experience. So every time I get to see something about water, I get really interested in it, so.
Yeah.
And I've learned a lot. For example, you guys may know this, but there's a word, and it's always pronounced key, but it can be spelled Key, Caye, Quay. And it's just like a place where a ship can go to land, you know, so it's like I would call it maybe a dock, or, yeah, I would call it a dock, but it's a little bit more specific than that. But that was kind of news to me, you know, and I do hear other people mispronounce it, like Quay or K or something like that. And then I feel like, okay, well, I'm not the only one on the world who doesn't know this, but I mean, I think so many people just historically, our human civilization has always been built on huge bodies of water and has depended on water for navigation. So the way that we live here is very unusual in the scheme of human existence. So maybe that's why I love bridges so much, but anyway, there we go. So in chapter 1, which is what we're gonna start on next, we really review a lot of things that we talked about in statics, but one thing I would like to point out, I know you know this, but it may not be in the top of your mind. If you have a structural member in a truss or anything else, the forces have to be directed along that truss, okay? Now, in other words, it can't bear something in a direction that it does not occupy in space. So the force diagrams that have the same geometry as the space diagrams. One of the things that we talk about in this chapter is the units of stress. And we also talk about the idea that there are two different kinds of stress. It doesn't mean that that's the only kind of stress, it's just that we define it in 90-degree angles to each other. So we define one type of stress as being normal stress, tension or compression, and then we define another type of stress as being shearing stress, which is back and forth, okay? So if you think about it, along the axis and perpendicular to the axis are perpendicular to each other. That's the big deal, because if you define stress in that way, in 2 dimensions, you have a complete description. You don't have to use the law of cosines. It's just X squared plus Y squared equals Z squared, essentially. So you can define the state of stress
So it's
based on normal and shear.
the shear and then is the normal. Like, so like if I have a joint right here, is it
Right.
normal like
Yes.
this way?
Yeah.
Like that's like if I was trying to pull it apart?
Exactly.
Okay,
That's exactly correct. So normal stress is either tension or compression. Shearing stress, we have to develop a sign convention for, but oh, trust me, we will. So that was good news. So continuing with that idea, we measure stress. Stress comes out, stress is a force divided by an area, which makes sense. This is kind of like when I was talking about my roof that my father-in-law designed, or you're talking about building something out of titanium. The other thing you can do to reduce the stress on anything is to make it have a bigger cross section, right? I mean, you take the same amount of load and you put it on a tree trunk rather than a toothpick, and it's not gonna matter. There's another one, a lot of times they talk about this, with, if you are walking, if you have a nice flat footed shoe, the heel impact, this is why, like, if you walk or run, it's very important to have good shoes. The heel impact and the toe impact will be distributed on the bed of the foot, okay? And everybody's particular footbed is different. However, that's the best way to not get heel strike or toe strike and get yourself into fasciitis, because that's how you distribute the stress. There have been studies done where the hardest thing on a floor, for example, is if somebody wears a very pegged heel, like a stiletto heel that you'll see sometimes women will wear. Yeah, stress is incredible.
Have we done a, like, math problem about that?
Yes, we have. So, yeah, so back in the day, we talked about that. So you have a good memory. It's true though. But so even like if you take a woman's shoe and you get a larger heel like this, you have much better, the stress becomes tiny, but the stress becomes tiny compared to that stiletto heel. But if you ever look at a woman who's walking in a shoe like that, it's hard on the foot and it's also hard on the floor. So, and actually when if you ever go to buy flooring, like hard flooring, they will sometimes do a demonstration where they'll put a piece of it up and then they'll pound on it with a woman's high heel shoe, because that is like the most impact that you can get, because you concentrate everything that you do in that little bitty area. So there you go. Just some things to think about. So stress is measured in force per area, and the unit for that in the SI system, a Newton per meter squared, is called a Pascal. And a Pascal is so tiny. 1 Pascal is almost nothing. So we mostly talk about KPA, MPa, and sometimes even GPa. All right, so I don't remember, let's do a conversion. An atmosphere of pressure is 14.7 PSI, except for here, because we're up quite a bit higher. But if you were at sea level, a typical atmospheric pressure would be 14.7 PSI. What is atmospheric pressure in pascals? It's a bunch. Yeah, see, 101,325. So just,
KPA.
yes, 100 kPa, 101 kPa is exactly correct. So in other words, a Pascal, if you think about 14.7 pounds per square inch, which is a more unit that we're more familiar with, that's the same as 101,000 Pascal. So Pascal is an itty bitty unit. We don't often use Pascal. Almost always comes with a multiplier. So just so you know, this is just an analysis and design, which we'll go through a little bit, but what is design? Well, if you know a stress, or you know stress you want to design for, how big does something have to be to bear that stress? You know, what will the stress be on a structural member if it's round and it has a radius? If you do that, P over A would just be pi r squared. You know, so in other words, it's just a cross section. That's all we're talking about here. It gets a little more complicated, and so you can design, like you say, what my radius needs to be by backing that out of that calculation, right? So when we talk about that, we're talking about axial or normal stress. Normal stress is what it's generally called, but axial just means along the axis. So that's how that is defined. You actually have, if you push on a member or you pull on a member, you actually have a stress profile that looks like this. So in other words, depending on the nature of the load and the nature of the material, how malleable it is, how bendable it is, you will experience an increased stress right at the point of application of the load. So when we say when we say sigma, which is a symbol for normal stress, is equal to P over A, we're really talking about average stress. For normal stress, average is a pretty good calculation. When we start getting into shearing stress is a little more clever than normal stress, but we'll use averages for a while, then we'll think about it. But if you really think about it, like if you have two structural members that are bolted together and you put them in shear, in other words, you work against, not along the axis, but perpendicular to the axis, all of the stress is going to concentrate on the bolt, all of it. You know, I mean, there's a little frictional desire to not give between the two boards or whatever you're bolting together. So shearing stress tends to concentrate. And you know, the expression, a chain is only as strong as the weakest link, that's totally true when it comes to shearing stress. It will find the weak spot and it will break there. So you have to design for the maximum stress at the weakest spot. So,
My grandpa taught me this when I was like
yes,
9,
yeah,
because his square baler,
yes,
there's like 2 chains.
yes,
Sprockets, and they have a shear bolt, he called it.
yes,
And he kept breaking the shear bolt because something else was binding up the
Yes.
machine,
yes.
so
But you want the shear bolt to break.
rather than.
Right. Right, as a matter of fact, you know, we have a minute, I'm gonna go back to my office, I'm gonna find something really quick, I'm gonna show it to you because it plays into exactly what you're talking about. So in terms of the video, I'm just gonna pause it for a minute and I will be right back, okay? I'm still not gonna keep you guys late, I promise, but you got me interested when you just said that, so I'm gonna show this to you if I can find it.
Oh, like probably one thing to think about inside is like. Probably won't work to fail before it feels like you want the 5 cent bolt to break before the, $200 ampere or whatever.
So, you know my little yellow truck?
Yeah.
The time it came broke,
No.
I think it did.
Yeah.
It might not be dead. If the valves and pistons, if it's an engine where the valves and pistons don't hit each other. But I think they probably did.
Oh, that's sad. The nice thing about, my truck is, there's no time changer mechanism, it's hard to gear together. Which is very nice, cause then it's like. And it does, it's a, I think the term is OHV, so it pushes the rods. But.
Yeah, usually like in gas motors, they don't do that because it's a little bit noisier.
Yeah.
But.
In a diesel, you're making so much noise, you're not gonna get it. Yeah. And like. And then it also has a crankshaft position sensor and a cam position sensor, and if either one of those goes, the engine will close up and not let itself be started back up. So that's like, people are like, it's never left me on the side of the road except for with the camera.
Hiding on me. I'll find it today, so. Yeah, hang on, let me. So I was not able to find the gear that I wanted to show you, but I'll look next time, it's just somewhere. Buried in my office, so we'll see, but it's what you're talking about. I mean, what you want is, I think of it as an analogous feature to being a fuse in an electrical circuit. You know, you don't want to kill the whole electrical circuit, you want to blow the fuse before, anything happens. It's going to cost you millions of dollars to fix. So it's the same when you have the gear system I have it's called a shear pin, and it's just supposed to be softer so that it breaks instead of everything else breaking. But some ingenious person took the shear pin and put it on a lathe and made something out of a stronger material so that it wouldn't break, and then the whole gear blew up. So it's awesome, but I wish I could find it right now, but I will find it, so.
It's so funny to me, stories like that.
Yeah.
If someone is like, this was a dumb thing that the engineer did, this thing
Yes.
breaks all the time, I'm gonna make it like.
Oh, yeah.
Stroud, so I don't have to deal with it anymore. And like my dad was telling me, there was some building that the engineer once built in like a specific way. It was
Yes.
almost like backwards from like the top down. with
Yes.
bolts or something like that. And they didn't do it, and like, because they were like, oh, well, we could do it a lot faster if we just do it this way.
Right.
And when they actually had it taken together, they had like a big opening or whatever, and like the entire building just.
You
Yeah.
see, isn't that
Yeah.
horrible? I know, stuff like that happens, and you know, it's like, everything fits together, that's why they pay you guys the big bucks, that's why engineers get paid money, like I said, I've never seen an engineer get paid, like, I've never seen anybody present a problem that says, you have, you know, I mean, like you see in your textbooks, the textbook problems prepare you for the problem solving that you're going to need, but everything figures in, you know, I
Yeah.
mean, everything, you cannot, and if you're a design engineer, you get to focus on certain aspects, right? But you have to deal with reality at the same time. So, I mean, and a building that you can build, like, here's another one. And I probably got some pictures of this somewhere, I haven't thought about this, but like, we got to go to Iceland a couple years ago. I took a trip with some students and with some of my family members. And the largest city in Iceland, Reykjavik, we went to some other places as well, but it's still quite small, it's like 30,000 people or less. But everything there, you know, like I was expecting like little Cape Cod houses, little, you know, shake roofs and little, everything there is built like a bunker. Everything is built like out of concrete. I mean, and the windows, like nothing leaks. You do not, when you're in a building, you don't hear an air passing outside. It's like a concrete bunker. Well, the reason is it's in the middle of the Arctic Ocean, right? And it's also basically a pretty denuded island with volcanic glass all over it. So when the wind blows, you also get these tiny little particulates of like abrasive matter. So everything that's wood or painted gets torn up.
Yeah.
Right, and goes out, to just goes back, so everything is built in this, I mean, it feels really cozy, you know, when you're there, I mean, it's like you go in a coffee shop and it's like, you just feel like you're in, you know, you're in your little cozy home because everything is nice, but the weather is, I guess I would call it ferocious, even by Wyoming standards, you know, so anyway, so you have to build based on, like, if you go to a tropical environment with a lot of flooding, you know, you'll see a lot of houses built on stilts, and I guess maybe those were the kind of things I expected to see, you know, like, and it was like, no. We're building it, sitting here, we're gonna dig it down into that volcanic, you know, that good solid volcanic stuff, and we're gonna build stuff so that it will never wash out to sea, so anyway. But yeah, so you have to build for a particular set of circumstances. Now, the next type of stress that we're talking about is shearing stress, and it has the misleadingly same equation, force over area. Okay, the only difference is that the force is not the axial force. The force is what, and the area could be the axial or it could be the cross section, probably is, but it could be a bolt, it could be, you know, just a shearing on a head, or if you have two bolts holding something together, maybe it's the surface area of both. So it requires a little bit of analysis, you know, to think about where's that shear going. So that's sort of I always say that's like a misleadingly easy equation. It is true, but what is the force and what is the area? So when we start out in chapter 1, so like right here, we have a bolt in shear, right there. If you pull up on this and pull down on this, the entire stress is going to be supported right here on that cross section. Okay, so it just shows you some different configurations of stress. Now, you can think about this, and you can talk yourself into a little bit of, I would say, concern that it's too confusing, but it's really not, because we're going to take everything piece by piece. You know, we're going to introduce some concepts, work with very limited situations, and then build up our discussion as the semester goes on. But the symbol for shearing stress is tau. And as you see, we have the AVE because it's average, right? And then we have to remember the geometry of the situation, okay? A bearing stress is kind of interesting as well. We talk about, there's sort of a cross-sectional area that we if you have something placed in, like if you put a wood peg or something, the area might be a little bit different, but it's just one more thing to think about. And then the same, we talk about application stress on structures, you find out where you're talking about that load being borne. So like if you had a structure like this, the first thing you would do is to do method of sections, method of joints. I would probably do joints here, but you want to find what the stress is, for example, in that diagonal piece, and what the stress is in the horizontal piece. And then you use that, excuse me, I said stress, I was incorrect, force, whether the tension or compression in those two structural members, and then you could calculate P over A based on those loads. Okay, and if you look at this too, this is just FYI. You would look at a normal stress here, but when you look at this bolted piece right here, you'd be looking at a shearing stress, right? So we won't require a lot of sophisticated thinking right off the bat, but kind of get used to the terminology, sigma, tau, normal, shear, and then also think about the ideas of different areas and then think about the units. So that's really what this chapter is working about. Now they talk about this method of problem solution. And so they just talk about this idea that you have to carefully check your answers and you have to use some sort of a reasoning ability. So to me, I find of all the subjects that I teach, mathematically, mechanics of materials is the easiest. But, throw a caveat in, it just requires that first real surge in engineering thought process, because you have to do a little bit more analysis. You can't just look at the equation and apply it to a situation without thinking about what's going on. So it's a good class in that way, but fortunately the math is quite a bit easier than, for example, in electric circuit theory, or I don't think anyone would tell you that it's easy. The math is not easy, but here we're confronted with math that's quite a bit simpler. All right, so then we get into some problems just to test your understanding of the material. And we finish up looking at oblique surfaces. And okay, so this section on oblique surfaces means, what if you have like a splice? You have a beam, but instead of looking at what's going on in the perfect cross section, what if you have a glued splice? That's really where stuff's gonna happen, right? So how do you analyze that? And this section just shows you how to do that. The only thing I would say is be careful to notice, because I don't know why 30% of the students miss this. The angle between the splice and the cross section is theta. And half of the time students will use, or 30% of the time, the students will use the angle between the splice and the horizontal. These equations apply to theta from here to here, not theta from here to here. So those two add up to be 90 degrees, right? So just keep that in mind. You can rederive these equations if you're committed to using this angle, but you have to realize that sine and cosine are going to be reversed in the problems, okay? Or I shouldn't say reversed, substituted. Another thing, once again, we get into this pretty, the symbology and so for example, here it says sigma is equal to F over A theta. So you'll see an A0 and an A theta. A0 means straight up and down area. A theta means on the cross section. Okay, so what they do is they use a little bit of trig so that you don't ever have to compute A theta. You only use A0 with some sine and cosine functions. Okay, but just keep them straight in your mind, because you can mess yourself up doing that. But they go through, they reduce the equations, and they come up with two nice little equations based on the theta between the cross section and the oblique section and the angle that they form. Okay, we talk a little bit about general loading conditions, and we will do a little bit about three-dimensional stuff, but we really focus more on two-dimensional stuff in this class. And the last thing that we talk about is a factor of safety. And I alluded earlier to the fact that my father-in-law had a factor of safety of about 12, right? I mean, I could take 12 times load on my roof that it actually was ever going to bear. But in real life, you always calculate what you really think are the answers and figure in everything that you think is going to happen. And then you multiply it by some other number and design for the higher number. And that's called a factor of safety. So in other words, generally speaking, a factor of safety in not static, the class, but solid load bearing designs is 2.5. That's quite typical. In the airline industry, they use the same idea, but they refer to it as a margin of safety. And a factor of safety of 2.5 is the same as a margin of safety of 1.5. So in other words, they just subtract out the actual calculated stress. And then they add to it the overabundance of caution, okay, rather than figuring the two together. But always, there will always be a factor of safety. So the allowable load is what you design for, and the ultimate load is the allowable load times the factor of safety. That's really what we're talking about. So ultimate stress or ultimate load is something that you should never, ever, ever actually have happen. That just means you're having a horrible day, but fortunately you had enough foresight that it's not gonna ruin everything in your life. So, and here's what it says, selection of an appropriate factor of safety. And as car guys, you guys are probably very aware of this, right? You want something to fail that's easy to get to and cheap, right? I mean, if something is very deep, I don't know if you guys, I mean, this is so far before your time. But back in the 1970s, there was a little car called a Vega. And in order to change the back spark plug, you would actually have to pull the engine, right? That's terrible design.
Yeah.
That is a terrible, terrible design. There's so many examples of good and bad designs in automotive, but that's one. You don't want to ever do that. You want things to fail where they're easy to fail, they're easy to get to and relatively cheap.
Yeah, that was something we were talking about, because one of his vehicles, its tire chain failed, but
Oh, I had that happen before.
yeah, my truck does not have a timing chain. It is hard geared in front.
Really?
Yes,
How
and then it's an
interesting.
OHB.
Okay,
So the entire, like the pistons and the valves and the springs, everything, like if you ever have either one of those break,
yeah,
there's also a sensor for both of them to say,
Okay.
hey, something's wrong,
sure,
and it'll kill the truck. Like you could be going 70 miles an hour down the highway and it would.
forget about it.
Yep. Which, sometimes causes an issue, because it's like, I'm coming, like, I don't have any brakes anymore, what are you doing to me?
Yes,
But it will save you from a huge rebuild,
yes,
and one of the things that he was talking about was like a lot of times with gas ones, they use chains because they're a lot quieter,
yes,
but on a big diesel like that.
Right.
You're already
You're
making so much noise that
Right.
like, yeah.
it's like when you go through a drive-through to get a Coke at McDonald's, you have to turn off your engine because otherwise
Exactly.
nobody can hear you.
Yeah. Yeah,
Yes.
so be like, hey, I'd like a Diet Dr. Pepper. A what?
A what?
I'd like a what? Turn off your car.
Turn off your car, please, oh my God, you're making me deaf. Yeah,
So, I mean, it's a trade-off, but like,
well, right, but
it's a very, Yeah.
they're both, they're just, and they reflect different philosophies in how to handle things. I mean, they
Yeah.
also reflect technology at that time, and they reflect how things were tooled. I mean, there's a lot of different things, but the good news is that it fails in a way that is not going to obliterate your vehicle or obliterate you, which is really the goal.
Yeah.
Unless somebody hits you from behind because you're now have no brakes and you're careening toward the side of the road.
yeah.
Assuming that doesn't happen,
Yeah, and like,
yeah,
the other reason I say it's close to foolproof is because it also has a hydraulically controlled injector system and a very early one. So that one causes headaches a lot of times, but,
I can imagine, so,
and I think, how many miles are on that vehicle that you had just kind of?
So did you see the little yellow truck I was driving last semester?
yes,
That's the one the tire chain broke on.
okay, so is it?
I don't know yet.
I don't know yet.
I don't know if it like destroyed the rest of the engine or not, but, I have no idea how many miles are on it because the odometer only goes to 100,000.
So it's more than that,
Yeah, I mean,
Yeah.
it says 74,000 and it was still, but like, that could have been rolled over like,
terrific, yeah,
Lord knows.
4,000 times.
that's
Yeah.
awesome, yeah, well, that's I'm sorry about your truck. Yeah, I had, it was years and years ago, but I was driving from Denver to Casper in an old car. I mean, it was a 20-year-old Buick and time chain just snapped, just absolutely snapped. So pull over, get a tow truck, take care of it.
Pray that the cylinders are okay.
That's right, and everything
valves
was
are
fine,
okay.
yeah.
Yeah,
Well, it was like an old car, it was an old Buick, and those things were built like tanks, they were built like my roof, you know, I mean, so.
the old Buicks.
That's right,
Modern
exactly.
Buicks.
You know what, you'd open up the hood, and the engine was called a Wildcat, it was just a little two something, I can't remember. The size exactly, it was 6-cylinder, and you'd open up that hood. And the engine just sat in it like a little biscuit on the middle of the day, you know, so it was like you could get around it no matter what. I didn't prepare it
It's
myself,
like
I wanna be clear, somebody else had to do it for me, but you know.
So my first truck was a 5.4 V8 from 2001, and then actually my second truck is a 7.3 V8.
Okay,
And for a very brief moment during the summer, I had a small block Chevy.
oh,
And the difference in the head sizes were hilarious. Because
hilarious,
it was like,
oh, I'll bet.
both the Ford ones that I had, like you could like everything's on top and like. One was a lot easier to work on, the other one, like,
Yes.
if I find the guy who designed that. We're gonna have words of discussion.
It's one of the things I wish to have explained to me.
Right.
That's right, exactly.
Like, I could go through with the small block Chevy one, and I could go through and I could touch the wheel without having to like move
Really,
anything at all, yeah.
wow,
And it wasn't like a full palm, but like, you know, I could get a finger on.
that's
it, which was-
awesome.
Yeah,
That is awesome. I love that. That's great. So,
it's also kind of funny, cause it's like.
well,
my
the other
parents-
thing, I was just gonna say, for you guys working on cars, I'm just gonna say this I mean, this is just an aside, but, my husband and I were married when we were in college and he was always the car guy and we always drove old vehicles. And he always kept them running, and I think he saved us hundreds of thousands of dollars.
Yeah.
You know, so you guys will do the same. So it will allow you to go to school without getting indebted because you have to have, you know, a 2019 or newer and you have to have warranties, so good for you guys.
Well, that's
Good for you
like,
guys, that's good. And also starting here, what a great engineering
Right.
decision, holy cow, I gotta tell you, so.
Yeah.
Anyway, alrighty, well, I'm gonna go ahead and stop recording, but I'm glad you guys are here, and I think we talked about chapter number 1, so if you have any questions, like I said, you're still able to hand in the review without any penalty. But as you get going on your chapter 1 homework, if you have any questions, just make sure you get a hold of me, and otherwise, we'll see you next Wednesday. There we go, alright.